Everyone is doing the midterm season. So I received a couple of emails asking about MSAP. The labs. MSAP lab. You have 1 week. I know that MSAP gives you 5 days, but if you make it a week, you have 1 week to submit it after the lab deadline. Okay. So the midterm, as we said, happen, or if you have a reason, then you don't have to. You don't offer a new item midterm. The grade will go to the final. Right? For the reading, we had a discussion about DRAMs. Right? Again, looking for the bigger picture. We spent some time on the CPU itself, then we had the cache hierarchy, and then we went for off-chip memory. Right? Last time we finished, we finished the DRAM device as a device, how it's being composed of, bands, channels, etc. How does it work? How it gets data from it, the row buffer concept, and all these things, time constraints. And then today's lecture is going to be on the memory controllers. The memory controller is the block that is on chip, directly interface with on-chip memory. It's the one managing the DRAM device. We said make it low cost and control it broader. DRAMs are usually down, right? We don't do any intelligence. It's a very simple circuit. Most of the intelligence on the rescheduling, the reordering, handling reads and writes, getting the time constraints, state machine, all that stuff is in fact done by the memory controllers. The on-chip ID that exists at the interface, any requests that are missing in the LLC of the last level cache are going to go to the memory controller first, form them in the DRAM command, handling stuff, maintaining all the time constraints, and push the request to the DRAM. Good. Then receive the data from the DRAM and push it forward to the cache. Good. So that's the focus of today's lecture. But because it has been a couple of weeks, I wanted first again to refresh your minds about the DRAM device working, and then we go to the memory. Good. So we said last time that the DRAM is in fact composed of multiple parallel entities that we call them banks. A bank is a 2D array of cells. A DRAM cell, if you remember, is just a capacitor and a transistor, right? Very simple. And then the bank is a 2D storage array. We have columns and then we have rows, right? Then we have what we call a row decoder and a column decoder. What you do to access the DRAM is you feed an address in 2 stages. The first stage you feed in the row address, the row decoder, with the activate command, what we call the act process. You bring in the full row from the cells down to what we call the sense amplifiers or your row buffer. That works as a small cache holding 1 full row. Usually the row size is 1 to 4 kilobytes in most modern DRAM. You bring this full 2 kilobytes into the row buffer, and then in the second stage, you feed in later on in the cycle the column address to the column decoder that's going to pick a particular column or columns from the row buffer to read basically this number of bytes you request from the row. Good. And we said this is a cache operation, column stroke, column access stroke operation, the DRAM terminology, and this is basically read write. Good. These are 2 stages we discussed last time: activation and reading or writing. There is a third one, if you remember, right? That we said we might. Does anyone remember what is this third stage? Yeah. Losing just that. Yeah, the recharge state. So the idea is what we talk about right now is the bank is idle. Nothing that goes in the sense amplifier. We do the activation and then reading or writing. we said there is a better scenario, in fact, faster scenario. If you have an access to a data that already exists in the row buffer, in that case, it's a row head, and you only need the reading write. That's your best case, right? We call it a row head. But then there is a third scenario, which is your worst case, where you access the data that, in fact, other than the data existing currently in the row buffer. What you need to do in that case, first, recharge the data, the old row, to its original cells. Recharge means write them back to the original cells before you bring in the new row. And why we said we need this recharge operation? Because this is what Steven was saying. That simply a DRAM cell uses a capacitor to store the data. So if you read from a capacitor, like this is a draining of the charge, the destructive process, right? It's an invasive process. But by reading from the cell, you in fact destruct the data in the cell, right? So the one that is currently holding the right data is the sense amplified cell. Before you lose that data by bringing in a new row, you have to write it back to the cell. What does it mean to be write it back? Simply put the capacitor charge back to its original value. So I call it a pre-charge operation. Good. So these are the three main operations done by the DRAM. There's a fourth one that happens periodically. It's a refresh. We'll come into it today. Good. We discussed addressing as well. Yeah, so this is what shows you the hierarchy of the DRAM. Like similar to the cache hierarchy, you build the DRAM out of multiple parallel entities to maximize parallelism as much as you can or interleave. We said a channel is composed of multiple gaps, and then logically composed of multiple ranks. A rank can be composed of multiple banks, and bank is composed of multiple rows and columns. Right? When we say a DRAM bank, and this is something in fact I find confusing, even in people for people working on DRAM. So there is a logical representation, there is a physical representation. Like for example, when people say, I'm talking about the RAM, that's in fact a logical representation, right? What I mean by this, let me give you an example. When we also say a bank, that's a logical representation as well. Because when you say I'm accessing bank 0 at the moment, if you remember from last time, we said bank 0 in fact means you access bank 0 in all the chips, right? Do you remember how do we compose 64 bits as the interface? Simply you combine 8 different chips, everyone giving you 8 bits at a time, right? So to be able to enable this, you want to make sure that a single access will enable the chip select of all the chips, which means accessing bank 0 means accessing bank 0 on all these chips in parallel. So a bank 0 representation of this slide is in fact a logical representation composed of all the physical bank zeros for the chips. Okay? Okay, so now this will take us to the operations and talking about the memory controller. So again, what I was explaining at the beginning of the lecture to the memory controller, this is unit chip basically. So all of this is on chip and this is off chip. Your memory controller is the last module that interfaces to the CPU to send it out to the DRAM, right? Again, the first operation is I feed the row address to the row decoder, read the row to the sense amplifier, which works as more cache, that the act operation. And then second stage is provide the column address to the column decoder for a read-write operation. You read a particular column or multiple columns from the sense amplifiers, feed this to the output ports. Then after this is done, the data is being sent to the memory controller, which will basically, take it and then feed it to the cache hierarchy and to the CPU. And then the pre-charge operation we already explained. This is a graphical representation of the three scenarios you mentioned. Green is your best case, and red is your worst case. Your best case is you head into the row buffer, so you only need a read-write command. And from last time, if you recall, we said this is 10 to 15 nanoseconds in access time. Good. And then, the statement in the middle, the yellow one, is where your bank is idle. Basically, no data in the row buffer. So you only need an activate and then read or write. We said this can happen at the very beginning, where the DRAM doesn't have anything, or after a refresh operation that we're going to discuss in a second. Good. So if you refresh the DRAM, it retains all the banks to the idle state. In that case, you can activate directly because nothing exists in the row buffer. And then the worst case is you're trying to access a data that is different than the data existing again in the row buffer. You have to recharge first, then activate the new row, then do the read or write. So this is your worst case scenario. For a comparison, it's again 10 to 15 nanoseconds. This is usually above 100 nanoseconds. So there is a 10x factor difference between the best case and the worst case. That's why we said last time, DRAM, dynamic random access memory, it's in fact not random at all, right? Because it does not provide a constant access delay or latency to locations. The delay that a request will suffer to the DRAM heavily depends on the state of the DRAM, what bank you are targeting, and also the previous request for you. Okay. So this is some example of the timing constraints we also had last time. Here, A is an active bit, and then this is a write, and this is a read. So some of the examples of the timing constraint, if you activate bank 0, you need to spend TRCD time. This is called the activate to read or write time to bring in the row to the row buffer. So this is a physical meaning. These are the timing constraints dictated by the JEDEC standard that are going to honor the requirements of the physical circuit of the DRAM. So once I do the activation, I need that much time to bring in the data to the row buffer. So I cannot read or write before that. Otherwise, you will get garbage read. Good. In fact, some of the very interesting recent research directions, the people are leveraging these timing constraints to create random numbers. What they say is, if I don't honor these timing constraints and I read garbage data, it's likely a random. Right? So if you want to generate truly random numbers, you can play around with the timing constraints of the DRAM and use the garbage output to something that you don't expect, you don't know what it is, as a random number. Good. DRAM is used as a truly hardware random number generator. An interesting idea. After this time, you do the writing. Then once you issue your write command, you need to wait for some time again. It's called EWL. It's your cast to data time. This is the time where, if we go back to our figure here, this is the time that it takes for the sense amplifiers to read the columns and push them to the output pins, right? Here, I did the read command, write command. Take some time to bring in the data from the sense amplifiers forward to the bin. Right? This time for writes WL and for reads RL. So why they are different? Because for writes, you are in fact getting the data from the input bin to the DRAM cell. And for read, you are getting it from the cell in the out. Right? So different direction. And then once you do this, you transfer the data on the data bus. And then if you want to, that's another big problem with DRAM, in fact, that also didn't discuss last time. But it's relevant here because it impacts how we design our memory control. DRAM, if we go back to this bus here, this one, it's in fact a single bus. And it's unidirectional. It doesn't have both in and out. But you can change it. So basically, for a read, this bus will go to that direction. Well, apology. For a write, this is I'm talking here about the data bus, right? Data bus. Because you are providing the data from the memory controller to the DRAM, while for a read, your direction should be this. Good. This means going from a read to a write or from write to a read, I need to change the data bus direction. How do I do this? Well, it's a low-level electronic circuit. I'm not sure if you cover some of this in some electronic courses, but there is something called termination. Have you ever heard that term? Termination, resistors, and that stuff, right? Sometimes happen for RF circuitry as well and communication systems. So simply, if you have a link between two different circuits, there is something called termination to avoid the intersymbol interference. Like you are propagating something on your link, and then your circuitry can also provide some noise. So you want to terminate your link such that you don't create distortion, right? So the way you change the direction for the DRAM is you change your termination settings such that you make it go to that direction or go to that direction. Good. Now, this is again another physical operation, which means going from a read to a write or write to a read in DRAM would require additional timing constraints, right? So why, for example, if you do consecutive reads, because you don't change the direction, they can be very fast. But if you do a read write, read write, there is a very large overhead delay. We usually refer into it as the turnaround delay of the data bus because you keep changing the bus direction, right? This takes us to one of the memory control optimizations later on that it tries to schedule reads back to back and writes back to back, right? In order to avoid this turnaround time. Going back to our time constraints here, this is really what reflects this turnaround bus direction. After you must wait between the write to the read. You must wait for the time to transfer the data, the time to start transferring the data, then the data transfer itself, then something called write to read switch, and then only then you can send the read. Compare this to the fact that if there was a write back to back, in reality, the constraint is something way less. It's called PCCD. So I can send another write here if I have a write. If this was write one instead read one, this is basically called TCCD. To give you some numbers again, this is usually 4 cycles in most DRAM. This is 9 cycles. This is 4, and this sometimes can become 7 to 9. Let's say 9. So if you add this up, 18 and 4, that's 22 compared to 4. So if you switch from a write to a read, I consume 22 cycles, DRAM cycles. Why back to back writes and why later on the controller will try to optimize this? I have a bunch of reads and writes, I split with them, something I send all the reads together, and then all the writes together. Good. Any questions so far? So what we're doing up until now is just a pure revision of what we did last time. So just to give you, again, some sense of variability, here I'm giving you the full timing constraints and tables for different access delays, like going to the same bank versus different bank, going to the same rank versus different rank, a read after a read after a write, if it was a hit, if it was a conflict. There is, in fact, a state space, a bunch of possibilities, right? Sometimes, I guess, 20 possibilities, where 2 consecutive requests can be getting different delays, right? And then I draw here, well, the time constraints, or the time it takes the second request to fail, right? For example, the best case here is you have a read followed by a read, and they are targeting the same row, different column, which means it's a row head, right? That's your ideal best case. There is no bus turnaround time because it's a read after a read. It's a row head, so it's a minimum time you only need a read command. So I get 15 nanoseconds. The delay is in nanoseconds. Compare this to the worst case scenario here. This worst case scenario is 2 requests. They are row conflict, so they are targeting different rows. The second one must reach the first one first, wait for the data, and then stop. And also, you can suffer read to write switch, right? Or write to read switch. So you also wait the turnaround time. It goes from 15 nanoseconds to 108 nanoseconds, right? Again, like a 10x, more or less 10x delay. Good. These are in fact true numbers using DDR4, right? Not hypothetical numbers. Yeah, here I'm just saying, well, the variability delay, this VW is the variability window is in fact 600% difference in time. Yeah, this is just an animation explaining the example we also had last time of I do the row and then feed it through the column, and then the data goes forward. If I have a row head, then I'm targeting row 0. So my data is available in row 0. I only issue, so this is a head. Then I issue a cast command only, and then directly read from that row. Now, if I have, that's another row head. Then if I have a row conflict, what would happen is I have first to pre-charge. So this is a conflict because I'm targeting row 1, while what is in row upper is row 0. And then I have first to pre-charge row 0, send it back, and then activate row 1, and then do the read or write the cast command or the column command from that row, right? This is your worst case scenario. Any questions? So this is, well, this is a screenshot from a data sheet. I forgot what memory is that year to year, but it doesn't really matter. But I just wanted to show you how things happen inside the devices. So here, for example, you see the different banks of chip, bank 0 to bank 7. So you have 8 banks. Here are the sense amplifiers, right? Then if you look into the boards, DQs are your data, like these are called data lines. So you basically have, and DQS is just a clock for the data. So you have 8 bits of data, right? And here are your address things. Remember, we said your address things, because you multiplex the address, even if you have 32-bit address, you send it in 2 stages. You need this number of bits. So here you have only is equal to 15 bits, 14 bits, and then this one, the 10 bits, 3 bits. So in total, you have 17 bits for your RAM. But this 17 bits can allow you to send 32 bits of data to address. The reason is you first send the bank bits and the row, then afterwards you also use this age to send the column address in the second multiplexes. This is one of the reasons of the high delay in the data. Yeah, this is showing you the example of a DEM, right? Where a DEM with 64-bit bus and then it's composed of 8 chips. Yeah, this is an example of a multi-channel DRAM where you have 2 different memory controllers in your one chip. Everyone is controlling a separate channel. A channel can be composed of multiple DIMMs, banks, multiple chips, multiple banks. Within the chip, you can say they have the bank. The bank is composed of array with them. Another representation of the high-level hierarchy of the DRAM. Yeah, this is also saying if you have the dual inline memory module where you have chips in both sides, usually if it's dual rank, in one side you have rank 0, and the other one side you have rank 1. So remember last time we said there are multiple hierarchies of DRAM, and this will make them semi-independent. So you are able, for example, accesses to the same bank are purely sequential, right? Because you compete on the same bank. 2 different accesses to 2 different banks can be overlapped. So you do some pipeline, right? Then we said, even if the 2 requests go to different ranks, that's in fact even higher parallelism. So there is less constraint on this. And we said the complete independence is if 2 requests go to completely separate channels, right? In that case, they can go hand in hand, no constraint whatsoever, because they access completely separate circuits, right? So in the same cycle, you can serve both of them. Here, it's an example of the parallelism of the rank, and it's also a justification why even ranks are not truly independent, right? Because within a rank, even if in fact you have separate data buses within a rank, at the end of the day, you would have a mux that simply only chooses 64-bit of data at the end. So at the end of the day, you multiplex on the data that you select, either from rank 0 or rank 1, and ranks in a channel share the address command bus, right? So you cannot really send 2 different commands to 2 different ranks on the same cycle because there is a single bus that really handles the access, the address, and the command. Good. So they're not 100% independent, right? Yeah, this is the example I also drawn by the Ben last time on how do we obtain 64-byte interleaved across different banks, right? We said I have a 64-byte cache line that's amiss in the last level cache. I need to get this from my DRAM. How do I get it? First of all, your data interface of the DRAM, your data bus is 64-bit, which means it's 8 bytes, right? What does it mean? It means that in every single cycle, in every single, let's say cycle for now, you get 8 bytes, right? But there is a caveat to this, is that in reality, DRAM, if you remember, we called this DDR, right? Double data rate. So you don't send data only on an edge of a clock, but you send on both edges, positive and negative, which means in a single cycle, if you have an 8-byte bus width or 64-bit, how many bytes I can send in a cycle? 16, right? 8 on the positive and 8 in the negative. So in total, this interface can give me 16 bytes every cycle. That's because of the DDR, right? Good. Then we said that there is a concept that we call in DRAM the burst length, operating on burst mode, that a single command is able to read not only a single cache, but not a single column, but a sequence of columns, right? And we said in modern DRAMs, DDR4, for example, the burst length is 8, which means a single cache will read 8 consecutive beats, right? So you do the operation 8 times. But the idea is because you operate on both positive and negative side of the clock, these 8 ones will happen in reality in 4 different clocks, right? So here there are 2 beats. So this is burst 0, burst 1, burst 2, burst 3, and you end up doing up until burst 8. But those bursts, every single one of them is in fact 8 bytes, your interface, and 2 of them takes 1 cycle because of the data, DDR, right? So in other words, just to put the summary together, to determine how many cycles it takes 8, and then that means there are 8 beats. How large is a beat? It's your data bus interface, so it's 8 bytes. But because you have double data rate, you don't take this gives you 64 byte, but how many cycles you would take? You wouldn't be taking 8 cycles. You would rather be taking your burst length, the number of beats over 2, which is basically 4 cycles because of the double data rate. This is because of the DDR. Good. So again, the total data size you transfer is your burst length multiplied by your bus width interface, 8 by 8, 64 byte. And how many cycles you take to transfer this is I transfer 2 beats every cycle. I transfer 8 beats. That's a total of 4 cycles. Good. Is there any question? Yeah. Yeah. DDR by default. Oh, yeah. There is no way you can get a single byte out of the DRAM. Yeah, that's true. So now the question is, or the other bit of detail is, how do I even obtain these 64 bits, right? Remember, we said we do this by enabling the chip select of multiple chips. So here we have 8 chips. Every single one of them is providing an 8-bit, which is giving me the total interface of 64 bits. So a single command, a single request from the memory controller will enable the chip select of all the 8 chips together, will be reading 8 from each, will be combined, concatenated into a 64-bit bus interface. Good. Is there any question? Okay, the only small note here is that here we are talking about a DEM, which is usually used in laptops, desktops, servers, etc. In a component or a discrete component DRAM device, something like you have in your mobile phone, for example, you can have, in fact, a smaller interface width. Instead of 64-bit, for example, in memory devices, you can have 16-bit memory or 32-bit memory. How do I control this? Well, you select this number of chips in parallel. So instead of having 8, if I have 4, this gives me a 32-bit interface instead of 64. If I have 2, this gives me 8 and 8, 16-bit interface instead of 32, right? So I control how many chips I have in parallel to basically give less number of data. Good. You have questions? Okay. Yeah, this is the example of the overlapping or pipelining that can happen. The same bank, simply are purely sequential. So you send a request, you wait for the data to finish access, and then you send another request. When accesses to different banks can go basically put a very and can overlap. Now this is talking about the address tracking that we also covered last lecture. Similar to the cache, where we need to extract the offset, the index, and the tag. Be able to, for the memory controller to be able to send the request to the DRAM, you need to determine what we call the segments of the DRAM. What bank am I accessing? What rank? I might have multiple channels, multiple ranks, multiple banks, multiple rows, and multiple columns, right? So which ones I'm accessing at the moment? I get the address from the CPU, and I do an address translation to extract those segments, right? How do we extract the segments? Well, the memory controller will deploy something that's called understanding, and it will be configured by a certain type of configuration. You, as a user, in fact, this is something that can be configured with a bias as well. You tell the user that to make this space to be a column, You pick these bits to be the row, you pick these ones to be the bank, etc. Right? And then you do a bit masking from the address to be able to determine your difference. Yeah.
Keeps track of which data which of the memory control.
Yeah, well, the address mapping is what defines this because the address mapping is one-to-one, it's unique. And I guess this is a very important highlight, is that address mapping doesn't change across records, doesn't even change across application. The memory controller is deploying one address mapping for one memory. So for every single request, there is only one particular location. It's a one-to-one mapping where you can be mapped to. Right? It will always be the same. True.
So what happens when if you add more RAM states to your machine?
Yeah.
It just maps more memory.
True, that's a good point. So assume, for example, your desktop or laptop enables you to add other channels or DRAMs or something. So the memory controller at boot up time, when it initiates, there is something called DRAM initialization. It would happen when the system boots up. It recognizes the additional hardware. And based on this, the memory controller would be able to call an address mapping to extend. For example, I added a channel, so I extend the channel bits to be able to address those, right? So at boot up, the memory controller will handle its own address mapping to recognize these new ones, right? But they still will be a one-to-one mapping. Any other question? Good. So here, there is some discussion on how to come with this mapping, because in reality, there is no one correct configuration. One can say, I always, aside from the basic, like the bytes and the bus, are basically your 64-bit, right? Or your 8-byte bus width, which takes you the opposite 3 bits. Where you put your column bits versus the row versus the bank is something that you can in fact configure. So if you, what is the implication of performance? If I choose my column bits to be here versus choosing my bank bits to be here versus channel bits to be here, right? And there is a trade-off, right? It's an interesting starting to do, but there are general guidelines. So unless maybe it's good to discuss this a little bit. And to simplify the scenario, let's say we only have banks, columns, and rows. So it's a single channel, single rank. Good. So some possibilities could be, again, aside from this offset thing, you put your column here at the least significant, then you put your bank, and then you put your row. Let me first ask you, from an application perspective, with the locality concept where most of the computer architecture is built on, do you want your row bits to be at the least significant or at the most significant, and why? Yeah. Yeah. So okay. So let's think on that. You are in the right direction, but I think you flipped it. So if I have good locality, which bits change the most first, right? So if you're accessing an array sequentially, the bits that change toggle the most are the least significant bits, right? If they keep toggling the most and you keep them your row bits, what would happen? 2 consecutive accessees will have 2 different rows. So you'll end up with a row conflict, right? So locality means your most significant bits mostly remain intact, are not changing. So most of the preference is you put your row bits at the most significant, such that they don't change as frequent. The reason for this is because of locality concept, you want to always target the same row. And because, again, I have a high locality, then the most significant bits don't change as much, right? With the same logic, where do you want to place your column bits? Yeah. Yeah. So changing columns within the same row, is this a row head or a row conflict? Yeah. It's a row head. Least significant, exactly, because flipping row column bits still keeps you within the same row, so you will be suffering less delay because of the row head. So most intuitively, most commonly used address mappings in your machines, for example, they place the column bits at the least significant and the row bits are the most significant, right? Now, there is a caveat to this. The row is done. It's at the most significant. There is no problem with this. But people are saying, okay, should I put column bits or bank bits at the least significant? if you put the column bits as the least significant, it means that the bank bits change the least, right, compared to the column, because again, it's a little bit higher. So these ones change the most. This one's change a little bit, and this one almost doesn't change, right? Which means most of your accessees are going to one bank, and they are hits. Good. The good thing about this is you are leveraging good locality. The bad thing about this is I'm not leveraging parallelism or interleaving because I'm going to the same bank. Good. On the other side, if I do a mapping like this, I put the bank bits first, then the column bits, then the row. This one changes the most, which means I open multiple banks. So I'm maximizing interleaving. But column bits change the least, which might be fine. In fact, I don't care about changing the column bits, right? As far as the row bits also are not changing, so I'm still row head. Yeah. True. But the point is that this depends on the application. For example, if I have a lot of high locality, it means that even going to the same bank will give you good performance because of the row heads. But if you have bad locality, going to the same bank will cause you conflicts. But remember, the row conflicts, you must be going to the same bank, different row. Across banks, there is nothing called row conflict because you have a separate row buffer. So in most applications, if you have less locality, you try to maximize interleaving, right? By putting the bank bits at the least significant.
Have bad localities, you're not gonna. Headers that are next to each other aren't gonna come up a lot, because it's saying they're bad locality. Isn't it a contradiction?
Yeah, okay, so I see what you're saying. But bad locality, it means also the most significant bits change, not only the least significant ones. So the rows will be different as well, right? So the point is, I want, when I suffer a row conflict, is to go across different banks, right? Just to parallelize my access, to amortize the high delay of the bank conflict. Good. So the overall high intuition lesson is there are multiple possible mappings, and this is all depends really on the application behavior based on locality and parallelism. There are different options to choose from. Good. Yeah. So it remains that there is one operation about DRAM device that we didn't discuss up until now, which is if we say a single DRAM cell is a capacitor and transistor, even if I didn't do any operation, you know from electronic courses that by default the capacitor its charge will decay and I will lose the data, right? So therefore, DRAM would require you to refresh. Refresh means simply recharge your capacitors every while, right? Such that your data is maintained. Good. So this refresh operation, what it does, it just does a very simple read. Like it's a read operation to just charge the capacitors back, right? But it must happen periodically because again, without accessing a DRAM cell, if you leave it as is for a long time, the data will be lost, right? DRAM refresh, because it's an overhead. It's only because how DRAM is designed. It has nothing to do with data access. It's in fact one significant source of large delay, but also of power consumption, right? This is one of the big problems of modern DRAMs. This is, for example, is not needed for caches or SRAMs, because in SRAM, I don't have a capacitor. It's like 6 transistors. The data will remain there forever as far as I have a VDD connected to the transistor, right? So don't worry about losing the data. But for a capacitor, I'm worried about losing the data because of the charge decaying. So I have to refresh the data. This is telling you that even if you're not using the DRAM, it still can be source of power consumption and additional delays. Okay? So there are two modes of refreshing. In fact, in modern devices like LP4 and LP5 and DR5, there are like baseline modes saying, okay, if I need to charge, the standard is telling me that for every single row, I need to visit that row for that cell at least once every 64 milliseconds. Every 64 milliseconds, I need to issue a refresh, right? This is really the cell. How do you do that? It's up to you. So usually there are two general techniques. One of them is saying, instead of really doing the bulk refresh of the whole DRAM, so one possibility to say every 64 milliseconds, I stop all the DRAM traffic, I don't accept anything, and then I refresh the whole device, right? The good thing about this is it's very predictable in nature. You know, basically every 64 milliseconds, you're going to wait for some time before you can access the DRAM again. The bad thing about it is that because you are refreshing the whole DRAM, it takes a lot of time. So if a read arrives, for example, a read arrives while you are just starting doing a refresh here. This unlucky read would have to wait for the full refresh, which is in fact a significant time. It's hundreds of cycles, right? So this is a very large delay. So the good thing about burst mode refresh is, again, I can predict it. It's very predictable. It happens in a very consistent time, periodically, takes fixed time. So you can account for it in your performance measurements for estimation at the application level. The bad thing is its worst case scenario is very, very high. If there are traffic coming directly before a refresh starts, it will stall for hundreds of cycles. Good. The other mode is the distributed refresh, which is saying, well, because the standard didn't constrain me to refresh everything together, why I don't issue refresh commands to single banks and rows amortized in time. So in this time, I do this row. After another time, I do another row. And by doing this, I'm allowing accesses to other banks as well. So if I'm blocking a bank for refreshing, I can parallelize accesses to other banks, right? So the good thing is it's distributed, so its impact in worst case, if I arrive here, I only wait for this small time. So its impact in worst case is minimal. But the bad thing about it is it's very frequent, right? Like you basically can suffer or cannot suffer. You need to quantify for it, right? So it's a little bit less predictable in terms of its impact in performance. Good. And this is one of still open problems of how people really, up until now, there are research papers coming out, and also there are industry solutions of how to amortize the refresh delay. Because there has been some studies that in reality, in modern DRAM devices, while the density is increasing, refresh impact is higher. And there are some studies that 25% to 30% of the DRAM time is in fact only consumed by refresh. This is as if you are saying you are wasting 1/3 of your DRAM bandwidth, right? Huge, right? That's very, very problematic, right? And also power consumption is very high. So people will try are having ways of really how you can allow to amortize this. For example, modern DRAM devices, again, LP4, low power started this, but then DDR1s, low power are the one usually you find in your mobile phones, and the normal ones are the ones in laptops, etc. So low power started this because they care a lot about power, and refresh is a very power hungry operation. They had the concept of refreshing a single bank at a time. So instead of blocking the whole DRAM, you refresh one bank and you can access all the other banks. And they also came up with the concept of enabling users to control refresh. So it's not an internal DRAM device circuitry, it's not a memory controller circuitry, but the user is saying, now issue a refresh, now don't issue a refresh. Why they do this? Because they say as a user, you know your traffic. So maybe during a certain time, you know that I'm not accessing DRAM, just leverage it for refresh. So it allows you to synchronize, orchestrate your traffic with the refresh. Good. Some of these techniques are deployed in DDR4 and DDR5. Again, it remains one of the fundamental problems in DRAM. Are we good so far? Yeah. So up until this moment, I guess we finished. We refreshed what we have done in the last lecture before the reading week, and we also discussed some new concepts for DRAM device. But we are done completely with the off-chip DRAM device. Let's stop here for like 10 minutes, and then after the break, we can talk about the memory control itself. Okay. Got a question? Okay, no, right. Yeah, I will post. I will talk about this after the break. Yeah. Yeah.
This is the first. Right? Then I guess the rest of the other banks can just use it. Like, since that accessing, but sorry, 16 bytes per clock cycle.
Okay, so here is where I believe this concept of a logical bank versus a physical bank comes into picture. These 8 ones, in fact, all of them together, like the first bank, for example, of every chip, all together is representing what we call logically bank zero. So bank zero, from an address perspective, from a controller perspective, is in fact a combination of all bank zeros for the chips. Because all these chips, a memory controller, in fact, does not have a visibility for the separate chips. It looks into the DRAM as one full input.
So this is one bank.
One bank.
Okay, so then in the case where you have multiple banks, which is like if you have different DDRs, 6 DDRs.
Well, I don't know, even same chip, you see that there are here these different boxes. These are the different banks. So for example, the first one here for all of them is bank zero. And the second one is
Okay, so then I guess then while bank one, while bank two is being accessed, all the
you
banks
can
behind it are.
you can replace the other banks.
So is there ever like a waiting time where like a bank's not refreshed? Like is that time?
Yeah, because what if you have traffic? Because we were saying also you're maximizing the interleaving opportunity of the bank. So most of the time, if you have a good memory traffic, it goes to all the banks. So this is the time where at one point you have to stop some of them, tell them I need to replace that bank now.
In terms of I been tinkering around with the so the repo you sent me is like 8 years old.
Okay.
And it's in Python 2.
Okay.
So a lot of like the actual like specific it's old, yeah.
Because recently, in fact, I saw another repo release that is using it's the most recent release.
Bit more like
Okay.
intuitive, just because like a lot of the libraries even like
Yeah, you
kind of
Python 2 is
yeah. So what I've been doing, like I guess independently, is like trying to just get YOLO 11.
Okay.
To work
Oh, it's
just for any image detection,
I see.
and then have classifiers like for like in the 8-year-old one where it's like dog, cat.
Yeah.
Maybe if you have it, send it.
Yeah, I will share that with you. I guess at one point maybe we should have a meeting.
Yeah, I was gonna say maybe
After you midterm.
after Friday, yeah. Not next one, the day after. I'll see.
Yeah. I will release them as well.
Yeah, I saw, like, I actually told you, DRAM lecture on your,
Oh, from last year?
yeah, from
Okay,
last year, but I still a little bit.
Yeah, the order is a little different. I follow the different order this year. But it's the same content.
Yeah.
But yes, I will post this report. Let me explain that to you. Assume, for example, you have an array. Because arrays are a very typical example of high locality, right? And then assume the first address spatial locality. And then also, in fact, temporal, because if this is an array of integers, then in reality, multiple entries will be in the same cache line. So you'll be accessing the same cache line multiple times before you move to another line, right?
Yes.
So assume you start with address 0. And then simply, second element, if these are ends, it will be at address 4. Right?
Address 4, yeah.
And then etc. 8, etc. Now, if you look into that, you will observe that these bits are the ones that are going to change the most before you flip the other bit, right? Like you see here, like this is 0, 0, 0, this is 0, 0, 1, this is 1, 0, and then after 8 you go to C, which also this will be 1, 1, right? And then only then you go to this one.
Yeah, so you're saying from here to here, they're gonna put.
Yeah, exactly. These ones, for example, flip the most. What about this one? Because this also can flip, but the point is because you jump in 4-byte granularity, usually this remains 0, right?
Okay.
But the idea remains the same. Is at least significant bits in high locality applications are the ones that are toggling the most. You agree?
I agree, yeah.
Great. So take this information and then think about a possible address map. Which segment of the address mapping, you want them to change very frequently. Is it the row or the column? If you keep changing the row frequently, is that better or worse?
Go in the DRAM.
Yeah.
Worse, because you want to finish
The data within a row before you jump to another row, because jumping between rows is a very high cost. What we call the row conflict, right?
So
You need to
free
feature exactly, right? Exactly. So for that reason, you don't want to map the row bits to the least significant bits. If you map the row bits to the least significant, they will toggle the most. They will cause you a lot of conflict, right? So according to locality, address mappings put the column bits at the least significant and row bits at the most significant. Great. Good. And then now the question remains between the bank and the column. Which ones you want to put first? When we say you put the column first, it means that you are favoring locality on the same bank because the bank will change the least. So multiple accesses will go to the same bank, but to the same row. So it's a row hint. You favor locality. While if you put the bank bits first, you are jumping across different banks because this changes the most. So you are favoring parallelism. True, right? True. And now which one do you choose? It in fact depends on your application. Yeah. That's all what we will. Great. Yeah, thank you.
But to start, I can wait till after.
Uh,
The lab actually. In this part 7 where you set the memory size, so it's the size of the like virtual cache, I guess, right?
yeah, it's the size of the memory footprint.
It's what you allocate, but then
Yeah.
versus the configuration, it's different. Right? The one thing I noticed is that in my analytical results, I explained how on pencil and paper, when this exceeds the size that's available in L1, then the temporal locality is destroyed because you're overwriting it.
Okay.
But the one thing I noticed is that the number of requests and hits in the actual like testing is larger than what's expected by on paper, and not in the other ones it's off by 1 or 2, and this one it's off by like 800 or 900. And I've checked with other people, like that's kind of general trend, like everyone's seeing a larger one. The only justification I could come up with is because it's 32 kilobytes and L1 plus L2 is less than 32, that the simulator handles that request. Is that fine in terms of justification? Because I couldn't think of any reason why, and it's just it's like a weird amount more. Like this is like than something more than this. It's not like a number that's like, oh, this is a part 2, like I'm missing something.
Yeah, I see.
Like I think it's just a simulator.
Well, in reality, okay. There is something we didn't discuss yet in cache that we planning to do in this lecture, but we took more time for the VM coverage. We are going to discuss next week. It's related to write back. If you remember the eviction stuff that we were discussing.
Yeah.
But when you evict a cache line and it's dirty, modified, you have to write it to the your next level of cache because you don't want to lose the
You
data.
have to pass it down.
Exactly. This passing down is a new request on it, right? Because it's, you created a request that would require if take this line, write it.
Right.
If you start evicting things from your cache because it's capacity, more of these replacement requests will happen.
Okay, but I think the simulator treats them as one request, because when you go, the eviction's also happening at 16 kilobytes.
Yes, but like basically the number.
Like, what do you mean?
Like basically because now you will have evictions from L1 to L2 and from L2 to a deal.
Yeah, but this is only tracking the L1 request to L1.
No, this is the total number of records. If you report what is being reported by the simulator,
Yeah.
is the total number of records in the system. So any replacement created anywhere part of it.
Oh, so this is because this is fixed because there's no L2 eviction.
Yeah, so basically,
Okay.
you see what I mean? It's less.
So my justification is fine then,
Yeah,
because we had
at the high level, that's good. I mean, you couldn't have him because we didn't explain.
we haven't learned about the
Exactly,
eviction
exactly.
policy.
So this should be good. If you ask me, I would add another sentence just saying that this might be because of the replacement happening because of eviction. Will the catch is small. That's all.
Okay, we already submitted, so
You don't have to worry about it because that's something I didn't explain. You
okay.
shouldn't worry.
So we lose marks on it.
No, you don't. You
I
don't.
wouldn't. I wouldn't.
Oh yeah, that's not fair.
Okay.
Okay. Okay. So one thing to mention to you about the midterm. So just a reminder that the midterm is on November 1st, right? 6 p.m. Again, I will send on Avenue a sheet where by name there are 2 rooms. So I will send a name and which room you should go to, right? Before the midterm day, you will know exactly what room you should be heading to. And please stick to your room because what we expect you to be there, right? The other thing is the midterm will be up until caches. So DRAM is not part of the midterm. Good. That said, there is one small part in caches that we didn't cover yet. And most likely when Ali was doing the tutorial with you yesterday, you encountered a problem that might be related to this, which is write allocation. What would happen with writes, right? If I have a write, do I allocate, not allocate? Well, do you do write back versus write through? So writes has 2 particular questions in caches that we need to address. And this is going to be discussed on Thursday's lecture next week. Good. Well, okay, I cannot put it in the midterm. Don't worry about it. It's not part of the midterm. Okay. So whatever we discussed about caches up until now is what is going to be in the midterm. Good. DRAM is not part of that. So the second thing is next week lecture, I will ask the TAs to come to the lecture tutorial to solve previous midterm with you and solve additional problems. So next week, we're not going to cover additional topics, right? The plan is I finish the memory controller today, and then next week, Thursday and Friday are mostly for revision. Again, solving the midterm will most likely take the Thursday tutorial and lecture. And then on Friday, we'll solve some additional problems and take questions. And the week after the midterm, we will start talking about out of order execution. So we'll go back to the CPU. Good. Just to give you more practice problems and see if you have questions. My sincere advice is to make the best use of this next week lecture and tutorial stuff. Try to solve the exercise problems we have posted for caches, for pipelining, for branch prediction, for performance estimation, such that you know exactly what you can expect from the midterm, right? And then you are able to ask questions during the tutorial and the lecture. Yeah, let me take that question first. I will post it on Avenue. Yeah. And that TA will solve it with you also next week. No. I will post it during the weekend. Yeah. Before you go, makes full sense. I will do that. Yeah, but they don't fully go through all questions because of time constraints. So there are some problems that are not solved, but I also post the solutions to you. So my advice is go through all the practice questions you have, right? Should be all fine. Yeah. No, yeah, that's also a very good question that I usually receive. There is no direct lab-related content, right? But if you think about it, all the concepts that you try to touch on the lab are in fact things that we covered in theory in the lecture. There was no new concept at all that we had in a lab, and that's it, right? So there is no direct lab question. But to me, In fact, any question that would touch on those exercise problems is in fact something that is also lab related. Like the lab and the lecture and the tutorial, they are very intermingled in that course, intentional, right? But there is no question in a lab. Every setup has its own type of theme. I cannot ask you to run an experiment in an exam, right? Yeah.
That's why I asked like format of the midterm, or I guess we can get off last year's midterm will be similar.
It should be similar. Yeah, it should be similar. There was another question. I usually give this advice, and many of the students fire back that they don't like this advice. But don't worry too much about the format of the exam or how many questions, etc. Because again, we are constrained by time. Like for example, I can give 3 questions. Like if you ask me, okay, how many questions? And that's a very usual question I receive, right? I can give you 3 questions that will need 3 hours to solve. And I can give you 10 questions that will only need 15 minutes, right? So the number of questions on its own is not an indication of anything, right? It's a factor of how convoluted is the question and how it builds a story and how much time it needs, right? So what I can guarantee you is that this is a 1 hour and a half exam. There is no way you can get questions to require you if you know the material, if you know the lectures, the tutorial, the exercises, etc., and you have done the labs. I cannot give you something that you would need after that knowledge 2 hours or 3 hours to solve, right? So if you only have what we have discussed in the course overall, then you should really have enough time to answer the questions, right? But my advice is to pay enough attention to details. Don't read solutions, because if you read the solutions, you ignore where the trick is in the question, right? You have to see the trick first yourself by going through it, struggling, and then only then you realize that there was something here. Good. Yes, there was another hand raised here. Yeah. Hit and miss chart. Oh yeah, yeah. That's one of the exercise problems that we also covered in the tutorial, right? So you get a sequence of axes and simply tell you what is the hit rate of the cache for that sequence of axes if you have a particular structure, right? You will see also this was a similar problem in the midterm last year. Yeah. Other questions? Good. Okay, so now we are left with the memory controller. So in reality, memory controller is an IB that is one of the most complex IBs in modern systems on a chip. The reason for this is we built a story about memory that in fact memory is a bottleneck. DRAM significantly or especially is in fact a significant bottleneck because of the very high access times, because of the power consumption. In addition to this, as you have seen, there are multiple states. There are timing constraints, there are hits, there are misses, there are banks, ranks, channels, etc. So there are multiple states you need to keep track of. And you need to optimize for that traffic. So you need to optimize for raw hits, you need to optimize for the bus turnaround time, you need to increase interleaving and parallelism. So there are multiple things that you can do. And unfortunately, DRAM devices don't do any of this, right? Just very dumb. Receives the request, do the basic circuitry to serve it. So all the effort is on the shoulders of the memory controller to be able to optimize your DRAM traffic. Good. So why DRAM controllers are in fact one of the complex IPs in modern chips, right? So now here, this is a very abstract view of a memory controller. So the idea is usually we split it into front end and back end. The reason is the front end is what is facing a CPU, as you can see from here. So I receive from the CPU a request. This request is, for example, an LLC mess is the format of an address and the type. I have something like 0xF3 ED something, and then this is a read or a write. Good. So now you receive a bunch of requests from different cores, if in a multi-core device. And because there are multiple requests, you need some sort of scheduling or arbitration. Multiple requests to serve, which one I should prioritize, right? So at the front end, you usually operate at the request level, or sometimes we call this the transaction level. While in the back end, where you are closer to the DRAM, you operate at the command level. So at the front end, you have here what we call, first of all, the address mapping. What is again the address mapping? What takes this address and breaks it down into what bank, rank, channel, row, column I access. Good. Why do I need this? First of all, before anything, because knowing your bank and your row will tell you whether you can be a row head or not, right? True. That's something very important to determine at the controller, because if you are a row head, you want to be prioritized before this row is being closed. Good. So you have well, a read queue and a write queue, and then you have what we call read-write arbitration. Again, why I'm doing read-write arbitration? Because DRAM has a unidirectional bus. Changing the direction of the bus takes a lot of time. It's the turnaround time. Going from a write to a read or read to a write is a very large delay. You want to arbitrate between reads and writes to minimize this turnaround time, right? So this part here is the one that is trying to maximize the efficiency by minimizing the read to write and write to read switch. Good. So if I minimize this, I save performance, I save bandwidth. Good. Then after I schedule reads versus writes, I do another selection. If multiple CPUs are sending you multiple reads, which one do I pick? So you do what we call transaction scheduler or request arbitration, where you pick from that CPU or that CPU. For example, in your mobile phone, if you have a Snapdragon chip, for example, from Qualcomm, you receive requests from a GPU and then from a CPU. GPUs are usually throughput oriented, so they send you streaming requests, while or video processing unit, they send you also streaming requests. While CPUs are usually latency sensitive, like they care about the latency of a request. It's a small request, only a cache miss 64 byte compared to, for example, 512 bytes for a GPU, but they care about the latency the most. So in general, there are requesters or processing elements that care about latency, and there are processing elements that care about bandwidth. The memory controller should be aware of this and doing a proper arbitration that will maximize the DRAM performance, but also pay attention to the separate processing elements requirements, right? If you're latency sensitive, you want to have high priority. If you are bandwidth oriented, you want to maximize row heads, that type of stuff. Good. All of this is done at the transaction schedule. Then once you pick up a request, so by the end of the front end, you have already decided one request to be serviced. Good. And you have already known that this request is going to this bank, this rank, this channel, this row, this column. What it remains is to translate that request to the low-level DRAM commands. DRAM doesn't take a request. DRAM takes an activate, a CAS, a pre-charge, right? A refresh, a bank address, and that stuff. So the memory controller back-end functionality is to translate a request to a command. Good. How do I know what commands do I need? Again, we have the cases we discussed earlier. If you are a row head, you only send a read or write. If you are a row conflict, you need to first change pre-charge, then activate, then read or write. If you're an ideal, you only send active. So the controller keeps track of all of this. In addition to the request information, what does the memory controller also need to determine what stages or what commands you need? I need to keep track of all the DRAM bank states. Because how do I know that I'm a row head? Even what does it mean to be a row head? What do you think? Now I have a request with this address and type, yeah? Exactly. So it means that your target row is the same row in that bank you target, and it's open. Who keeps track of this? The memory controller backend keeps a list for all the banks, and it has row bits there for the currently open row. So it says that for bank 0, row 0 is open. For bank 1, row 10 is open. When a request arrives, it does a comparison. If you have the same row as the open row, you are ahead. Otherwise, you are a conflict. Yeah, it's at the back end. In reality, this information should be used in two different places. First, to also prioritize the heads at the front end. Sometimes this happens. But most importantly, at the command generation stage, at the back end, this is being used.
Part of the command generation.
Yeah. Yeah. Good.
So would that mean the memory controller would tell the, if it holds something too long in the row write buffer, then it'll lose that information. So does it have to tell it to recharge again?
Yeah, okay. So what you are saying is if I keep a row open for a long time in the row buffer, you're saying I'm losing the because of the leaking? Yeah, well, row buffer it's a sense amplifier, it's not a capacitor, so you don't lose data there. The actual leaking happening on the cells themselves. But this is done with the refresh state machine. You don't lose data in the sense amplifier. Yeah, yeah. That's a good question. Good. Yeah. It's the location of the data of the row. But his point was in a, like similar to the DRAM cells, which is a capacitor that leaks data. Are we also leaking data at the row buffer? Last lecture, we said in reality, row buffer is an architecture terminology. It works as a small cache, but in reality, in circuits, these are sense amplifiers, right? These are only amplifiers to amplify the signal before sending it to the I/O, right? So they are not capacitors, right? They are amplifiers holding it. Yeah, well, there is no actual capacitance, but there is a storage because an amplifier, in fact, is transistor based, right? So you can still store the data there. Yeah, exactly. You don't have to leak. Good. Great. So at the back end, then I translate into the low-level DRAM commands. And once I do this, the idea also is different banks in parallel can have multiple commands being ready on the same time. What do we mean by ready? Ready means you satisfy the timing constraints. So also the memory controller has a state machine that we call timing machinery that keeps track of what command can be sent in this cycle. Based on what? Based on the timing constraints of the standard. Like simply, I have a circuitry here that keeps a table, says, I issued an activate at cycle 0. What is the earliest time I can issue a read to that bank? This is defined by that TRCD constraint from the standard. If I issue this act, what is the earliest I can issue another act? You keep track of all your timing constraints cycle by cycle, and this tells you whether for every command it's ready to be sent to the DRAM now or it can stall. Good. So right now, what did we say the memory controller keeps track of? The state of the DRAM banks by keeping a list of the open rows. It keeps track of the address mapping information to be able to translate it. The third thing is the timing constraints of the commands. For every command you issue, you have to honor the timing constraint by the standard to be able to issue another command to the same bank or to a different bank. There are many combinations, 20 plus combinations in a table, in a data sheet of the DRAM. Good. And the memory controller keeps track of all of this. Now, assume at one cycle, there is a command ready. Ready means it can be sent, the state of the DRAM is ready, and the timing constraints are being met. If it's a single command, you just issue it immediately because that's the only command you can send. But in reality, because you have multiple parallel entities, multiple banks, multiple commands can be ready simultaneously. Like, for example, a bank can send an act, another bank can receive a read right now. So there is an act to a bank and a read to another bank. But the point is that there is a single command bus. You cannot send two commands in one cycle. Which one do you choose, right? And for this purpose, we have here what we call a command scheduler. It's an arbitration that picks among the ready commands to pick only one of them to be sent on the command bus to the DRAM. Okay? This is too much story. So you start from a request, an address, and a type. You translate it into low level by the address mapping, so you know all the banks, ranks, etc. Then you want to translate this into commands, but this will require you to know the state of the DRAM, which row is open at which bank, in order to know whether you need an act, you don't need an act, and all that stuff. Once you determine this and all your commands are ready, all your commands can be sent to the DRAM, you have to make sure they satisfy the timing constraints. Like assume, for example, I did this translation and I realized that this address here is a row conflict. So it requires a pre-charge and then an act and then a CAS. So the command generation stage, which is this 5 here, will push this to what we call the command queues. So it will push a pre-charge command, an act command, and a CAS command to these queues, to that bank. Now, it's the functionality of the scheduler to determine at the top of that queue, if there is a pre-charge, can I send it at this cycle or I cannot? And if I can send it, but on the same time I can send another command, multiples can be sent. Which one do I choose? Good. Feel free to ask questions. So the DRAM lab will help you, in fact, see this in. So you are going to use a cycle accurate DRAM simulator that shows you all the translation, the command generation, and the queues and arbitration. So you'll be able to see that. Yeah. Yeah, it does. We will come into this. It definitely does. Yeah. So there are multiple reorderings, for example, between reads and writes, and between row hits and row conflicts, because you want to maximize performance.
How do we make sure that the command scheduling and the transaction scheduling are like doing opposite or like conflicting with each other?
That's a good. That's
Finishing up
yeah. That's a good question. So is there a way we can align those, or do we need to align them, or we don't need to align them? Definitely, there is some sort of high-level alignment that you are going towards a particular functionality. Most of the efficient implementations, the scalable ones, is that they decouple their decisions. They basically say the request scheduler takes a decision that cannot be overwritten by the command scheduler the other way around because it does something different. Just to give you a concrete example, request scheduler most of the time takes a request among multiple ready requests from multiple CPUs. So it says, for example, this is a request from a CPU and this is a request from a GPU. I'm going to favor the CPU one, fixed priority schedule, for example. This has nothing to do with the command generation of that request and which one is ready, right? So they are a little bit orthogonal in that sense, right? But that said, sometimes some request schedulers also look into favoring requests that are row hits. That's why I told you in the earlier question that this state machine of which bank has which row open can also be used by the front end, because some schedulers will look into this request targets an open row. I will give it higher priority to maximize performance, right? So sometimes it can be coupled and interrelated. But you're correct generally is that we want to make sure that we don't override their decisions.
its requests are coming from a high latency.
Yeah, based on these different ports. You don't care. Exactly, you don't care.
That's why the back end mess up that.
It might happen, but if you decouple their goals, like you make the front end scheduler at a higher or coarse grained between requests, while the back end only care about maximizing command performance, regardless of their type of request, then in that case, you get the best of both. Good. Again, as I said, you will see a lot of this in the lab, right? In a stage by stage. So hopefully it can give you better understanding. So now when we say DRAM scheduling policies, well, I will skip some of this, and because I have another better figure later on. Yeah, so there is one small note here, and then I will go to the scheduling figure. So as part of keeping the host state, to the DRAM, wow, the example we mentioned about bringing a row to a row buffer and then leave it there for further access. This is one particular policy or mode of DRAM operation. It's called request to bring in a whole row to activation to a row buffer, but you don't pre-charge it immediately. You leave it there, open. Why do I want to do that? For high locality concept, right? If a subsequent request targets the same row, will have better delay, right? So open row favors locality by leaving the data in the row buffer without pre-charging it immediately. But now, if you know that most of your traffic pattern is always random conflict, which means among the three, remember we had like this traffic sign thing. Among the three possibilities, this was the hit, this was the idle, this was the conflict. And we said this is around 108 nanosecond. This is 10 to 15 nanoseconds. And this is less than 50 nanoseconds. So if I have an application with very high locality, you are expecting most of the time you remain here, correct? So in that case, I will leave the data open in the row buffer to leverage it, right? But if in your application, you know that your traffic pattern is all random, all conflict, if you leave the data open, what you would expect subsequent requests to do? and activate the new one. So most of the time you would be here, right? Can we do better? But the idea of a closed page policy, on the other hand, is yes. And instead of being here, can I be here in the idle case? And this can be done by allowing a request. You open your row, you bring in the data in the row buffer, you do your read and write, but then immediately put the row back into the cells. Why do I want to do this? For the subsequent request, when it comes, it will find the bank in which state? Idle state, right? If I'm in idle state, I will suffer this delay, which is half of the conflict delay, right? So a closed row simply what it does, it closes the row directly after an access. The good thing about it, it's very deterministic. Every row does every access will do exactly what the operation. The bad thing about it, it does not have any locality at all. Closed policy works, or closed row policy works best for random traffic patterns because you cannot leverage locality anyway. Good. On the other hand, open row, the good thing about it, by keeping the row data open in the row buffer, you leverage locality, so you can maximize your row heads. The bad thing about it is that if your traffic pattern does not have good locality, then you're going to suffer a lot. Worst case delay of confidence. Good. For that reason, people in fact choose between row and open and close based on the traffic pattern. Good. Are there questions? Do you understand? So how the memory controller in fact deploys either of the policy? It's through controlling the commands you issue, right? For an open page, your request will have 3 different types. It can either be a read write only, or an activate read write and a pre-charge read write. So there are 3 cases. In closed page, the memory controller has a similar job. Every single request, activate, read write, pre-charge. In our laptops, for example, if you have an Intel machine, they try to leverage both. They say, okay, can I really dynamically change between open row and closed row based on my traffic pattern? So what they do is they deploy a dynamic or adaptive page policy where they keep a window, like they have a counter that they count the number of hits and conflicts. If the number of hits goes above a certain limit, it means you have good locality, so they leave the row open. If the number of hits falls below a certain threshold, then they say they have a bad locality, and then you switch to closed page. So they do it in a window-based format, which is dynamic, which is in fact pretty good. Are we good? So this is what we call a page management policy. Again, who is doing this? It's the memory controller as well. DRAM doesn't do any of this intelligence. Here there are some examples of the possible scenarios of open page and closed page and what would happen. So if you have an open row policy, and your first request is a row 0, and then next request is a row 0, this is a row head. The only command you need is a read. This is similar to what we had before. But if you have an open row, then you have row 0, but your next one is row 1. This is a row conflict. What do you need? You need a read, and then read. If you have a closed page policy, basically quite simple, because row 0 access and request buffer row head. Well, I wouldn't consider that this is disagree with this slide. This is slides from Modern Outlook. They have their own definition of closed page policy that is not necessarily what I would agree with. So this is closed row. If you have a closed row policy, and this is row 0 and this is row 0, in reality, there is nothing kept in the row buffer. So in that case, all of the time you would need an activate and a read. Access not in request buffer, row closed. Yeah, so you have an activate and read and pre-charge. So for every single closed page policy access, it's 3 commands: activate, read, pre-charge. Good. Yeah.
After the data back.
True.
So what happens if you have 2 consecutive?
Yeah. A very, very good observation. In reality, if you have them back to back, you didn't save anything. Both close and open would behave exactly the same, right? Because now instead of associating the pre-charge to the first of the second request, you associate it to the last of the first request. It just remains exactly the same. And also that if they are separated in time. So let me give an example for everyone. I guess it's a very good catch, especially if I didn't provide an example. So let's have the following scenario. I have an activate, and then I have a read, and assume sometime later on here, you have another request. And this request, this is row 0. Assume that this is targeting row 1. Now, if you have an open page policy, and this is after quite some time, right? So you satisfy all the timing constraints. If this is open page, what do I need to do here is a pre-charge, then activate of the new row, which is row 1, and then my read operation, correct? If this is a closed page policy, on the other hand, under closed page policy, the pre-charge is associated with the original request. So after the read, you in fact issue something called read with auto pre-charge. So it will pre-charge the row sometime here. Later on, when this request arrives, I don't need a pre-charge command. I only need an activate. And then I do my read. So by this gap, since you already charged the row, this second request suffered less delay. But if they are back to back, you are not saving anything. Right? Yeah, that's also a good point. But your pre-charge, and this is the point he was saying, your pre-charge is not really storing your CPU because you already transferred the data. So the point is this pre-charge constraint that you will do here has nothing to do with when the data can be sent. So the data can be sent to the CPU. Exactly. So it can be overlapped. Exactly. Yeah. No data path restriction. Exactly. Good. Okay. I need to. Okay, so if we understand the policy stuff, so we're going to discuss the scheduling in that technique. So basically, a memory controller has multiple levels of ordering or reordering, out of order execution of scheduling to maximize the performance and the bandwidth of the DRAM. So there are 3 levels of arbitration. The first one is what we call intra-bank arbitration. What is an intra-bank arbitration? Intra-bank, from its name, it's scheduling requests going to the same bank. So if there are multiple requests going to the same bank, which one do I choose? Now let's think intuitively about it. If you have multiple requests in your bank queue, which one can increase the DRAM performance? It's the one that is going to hit into the existing row of that bank, right? So within a bank, you want to maximize row hits. Remember, a row buffer is an artifact of a bank. Every bank has its own row buffer. So in that case, within a bank, I want to maximize or reorder requests that are hitting into the existing row, right? So if I have, for example, here, multiple requests that are, some of them conflicts and some of them are, like C here means it's targeting a closed row or basically a conflict, and some of them are open, targeting the data open in the row buffer, right? Just to understand this, you can think of the following. This is targeting row 10, this is targeting row 11, this is targeting row 15, and this is row 0, and this is row 0. And in my state machine, the bank state, for bank 0, assume that this is bank 0, the memory controller knows that row 0 is currently open, right? So if you were the memory controller, which request you would pick? So you have row 0 open. So you have row 0 open in your bank 0, and you have a bunch of requests that are in bank 0. Which one among these I will pick to send to the bank 0? What do you think? So based on what do I decide, right? So all of these are targeting bank 0, row 10, row 11, row 15, row 0, row 0. And the memory controller want to pick one among them. Yeah. And how this will help me? I will have it hit a row which will take less delay, which means I will maximize the performance, right? Exactly. So we call this first ready, first come, first serve. The idea is you prioritize the ready requests going to a row hit, right? Even if this arrives later on, you reorder this. You do out order execution by picking the ones that will maximize the performance. assume you didn't do this. What will happen? So let's have the two scenarios here. Assume I just move first come, first serve. So I will pick row 10. Row 10, and I have row 0 open. This is a row conflict. So I need to close row 0, right? So I will suffer. So this first request of row 10 is in fact a conflict request, right? So you'll suffer the 100 nanosecond we talk about. And then what about row 11? Maybe I will give you a more interesting scenario. Assume that this is row 10, this is row 0, this is row 10, right? If I go on first come, first serve, row 10 and row 0 is open, it's a conflict. So I close row 0, I open row 10. I'm done with it. I want to serve the second one. It's row 0. Is it a hit or a conflict? It's a conflict because row 10 is open, but row 0 is targeted. So again, I would suffer the very large delay of row 0. But what happens with the 10 one? It's conflict. So you keep ping-ponging between the two rows, suffering the very large delay of a conflict only because you stick to first come, first serve. Good. Now, on the other hand, if I do this trick of reordering the ready ones, what would happen? I have a bunch of requests in my queue, row 10, row 0, row 10, row 0. I see that row 0 is open. What do? I pick the one that is targeting the open row 0. So I serve this one first, which is very small delay. Then I go back again and try to choose. Is there another request targeting row 0? Yes. So you keep serving them very quickly. And then once they are done, you will open row 10. But once you open it, you will serve all the requests of row 10.
Memory or fairness or kind of calculator to determine after what point to stop.
That's an excellent point. That's in fact one part of the lab exercise. So up until now, we're talking about maximizing performance. We're not talking about fairness or how long a request that is conflict will wait, because the 10-1 waits for until all zeros finishes. In theory, in fact, this can be infinite because you can keep receiving row 0 requests from the CPUs. It's waiting forever, right? Until at least the refresh is closing the row forcibly, right? So this is a very large delay. It's too bad. So why most of the modern machines, on top of first come, first serve, they deploy what they call a cap. They say, I allow a maximum number of 32 reorderings, 16 reorderings, 8 reorderings. After this one, I close the row no matter what. And it's a performance versus fairness or latency or quality of service trade-off, right? Because row open, row hits, maximize performance, but it can keep some of the like conflict requests delayed for too much or even starve it, right? Good. So why there is a cap on top of this? Is there any other question? But at least we see how performance can be boosted by deploying this reordering. Good. Yeah.
Service for growth. Does it wait until that buffer is empty before refilling it, or is it like service goes 0?
Yeah, that's a good question. In reality, these queues, if we go back to our figure here, so these queues, every one of these queues operates on a cycle basis. So when you receive a new request from a CPU, if you have a space in your queue, you issue that request. And then once you translate it like into address mapping, etc., and generate the commands, you push the commands to the queue. So in a cycle by cycle basis, you can always receive new requests if you have a space. Yeah, always be filling if you have a space. You will only back pressure. This is called back pressure in computer architecture. You will always push back. I cannot accept anything if my queue is full. And in that case, it has to be propagated to the cache hierarchy and to the CPU, right? And that's a situation you don't want to do. Like you want as much as you can accept requests such that you hide the CPU by blind latency. Yeah. Yeah. True, which will cause a very large delay for the row 10 requests. So in that case, what if this was a latency sensitive request? Or what I was saying theoretically, what prevents me that I can keep accepting row 0, like the CPU keeps sending me This is, in fact, there is a very interesting study that this even can be used for denial of service attacks. Like assume you have two different CPUs sharing a memory controller. There is an attacker intentionally pushing very high streaming accesses that will always do row hits. It will, in fact, prevent the victim, the other CPU, from accessing that bank completely, right? Because all the time, I'm row hit, row hit, row hit, row hit, row hit, row hit. You don't have any time to access that bank, right? So it can cause denial of service. Yeah, at the memory controller side, you don't care about data dependency at all. I have well, other than targeting the same address. You cannot reorder, yeah, you cannot reorder reads and writes to the same address because there is a read-write dependency. Yeah, but a row is a very large. It's like 4 kilobytes. So there is high possibility that they are targeting different addresses anyway. Exactly. Good. Great. So what does first ready, first come, first serve do? We already discussed the first ready part, which is you prioritize the row heads to the open row. Now the question is, what if I don't have any row heads? What do I do? Everything is just a conflict. Then you go back to the normal first come, first serve, right? Whatever arrived first, serve it first. Then there is another question. What if all my requests in the queue are row heads? Which one do I serve first? Again, first come, first serve. This is why it's called first ready, first come, first serve. First, pick up the ready ones, and then among the ones on the same readiness, whether they are ready or non-ready, you do first come, first serve. Good? Okay? Any question there? Good. Yeah. Yeah. For example, there is something that is more into safety critical system doing round robin. Or if you deploy closed page policy, there is no concept of ready. There's always first come, first serve, right? Yeah. Yeah, but at the memory controller, you are abstracting this. Like there is no ISA concept. Exactly. It's more about a memory request. How do you serve it, right? This can be a load store, an x86. This can be a move with an address. To me, as a memory controller, I don't care. It's a last level cache miss. Oh yeah. It must be JEDEC stand. Yeah, it must be complying to the JEDEC timing constraints, satisfying all the commands, because it has to be correct from the DRAM perspective. No, that's a good question. First read, first come, first serve is a scheduling technique that is exact. It has nothing. You can deploy other policies as far as you satisfy the timing constraint. For example, if I favor the row head versus no row head, this has nothing to do with the. As far as I issue the right commands and I wait for the right timings, right? It's a performance optimization, right? Based on the applications and based on how the hardware is optimizing for locality or not locality.
As the memory controllers now on package instead of on chipset, the SoC designer has to choose this policy, and is this policy fixed to the architecture?
Yeah.
Physically implemented so that you can't change it?
Yeah, that's a very good question. In reality, yes, it cannot be changed. So when you pick a memory controller IB, part of the specification is that basically what the arbitration it does, how does it do it, what is the cap, and all of these things. Some of the IBs have the capability of being configured, but only statically during synthesis. Like basically when I deploy the IB into my, for example, you are an Intel vendor, right? Like building an SoC. And let's say you buy this IB from Synopsys, for example. Synopsys and Cadence, they're the two common ones with the memory controller IBs. So I buy it from Synopsys. Synopsys tells me, because they can cater for multiple customers, they tell me, when you generate your RTL, I give you some configuration. So I tell you, you can pick first come, first serve, or first come, first serve, or the cap can be changed that much, right? But once you synthesize your RTL, once you have the chip, it's fixed. You cannot change it.
Cheats the protocol when you're designing the chip, but once it's
like
physically manufactured,
you cannot change it. Exactly. Yeah. And there are some research papers on Is that really needed? Can we dynamically adapt things or not? Right? But still not being adapted. That's also like switching between like different policies can impact also things. That's true. That's true. Yeah. Okay, great. So we discussed first ready, first come, first serve. Remember, like what the higher picture is, we're only talking about arbitration of requests going to the same bank, right? But as you can imagine, there are also requests, commands from different banks, right? So how do I select between them? And this is the unique one. So this is the one here that simply says, I have multiple requests or multiple commands from different banks. Which one do I select between them? One policy, for example, is I do round robin cycling among the banks. Another one is to say, well, if this bank, for example, belongs to, if I do bank partition, like I assign banks to CPUs, if this one is higher priority, then I give this one more critical. I always choose this one, right? But the mostly commonly deployed one for this interbank scheduler is in fact round robin RR, right? Just cycle among the banks. Go to bank 0, pick a command, bank 1, pick a command, etc. Right? If it's definitely ready, which means it's satisfying time constraint. Good. That's the second level of arbitration. So the arbitrate first among requests is going to the same bank. Once you pick up a request, multiple banks can have multiple open requests, for example, that are ready to be sent. Then you have to select one from them. You will need another arbitration policy. Okay, and again, the one that is deployed usually is round robin. That's also the one that we do in the lab. So the third, is there any question? So the third one is what do we do with read and writes? The one that we started the other figure with, right? We have what we call write batch. Write batching is a very nice concept. In fact, it's deployed in different places in the architecture hierarchy. The idea of write batching is, first of all, we understand that the memory controller, that I don't want to switch direction frequently. So I want to, if I'm doing a read, I want to stick to reads. If I'm doing writes, I want to stick to writes, right? For quite some time. Because if I keep hopping between reads and writes, I will keep like switching the data bus, takes a long time. Pretty much similar to the row concept, by the way, right? Like again, for the ping ponging of the rows, like you don't want to keep switching rows. You want to stick, once you open a row, you want to stick for it for a long time, right? So just to give you an example, assume you have a bunch of reads and writes, again, in your queue. This is a read, this is a write, this is a read, this is a write. If you serve them first come, first serve, then, well, assume that you activate first and then you do the read, and assume all the subsequent ones are hits. If you want to do a write, you will suffer a very large delay. We call this the read to write switch before you can issue the write, and then a very large delay, a write to read switch before you issue the read, another read to write delay before you can issue the write. Good. So if this is first come, first serve. Now, if I do batching, like combining requests of the same type, once I do a read, I will issue all the subsequent reads. So here there are 2 reads, so I will issue them. And then if there are other reads, I keep issue them. And then finally, I do one switch, read to write, and then I keep issuing the writes. So you minimize your bus turnaround time to only 1 in our scenario. Okay? Yeah, row conflict is in fact one of the worst, but they are orthogonal. So it's not either or. You can have a row conflict, and also your row conflict requests are reads and writes. This goes back to the idea of a row conflict versus not, goes to the command backend because it's an act pre-cast stuff, while read versus write is a front-end request scheduling because it's a read request versus a write request. Like you can have 2 conflict requests back to back. One can be a write and the other one can be a read. So you suffer both, the row conflict delay and the read to write switch and the write to read switch. Does this answer your question? Yeah, definitely. Yeah. They are one of the worst. Like both are one of the worst for DRAM. So people, this is why there is a lot of focus on minimizing both. Good. You can see that minimizing the switching here can help you, in fact, finish way earlier, right? Because I give you some numbers like write to write or read to read is usually 4 cycles, which is just your data bus transfer time. But this one read to write is usually 9 cycles, and this one is usually 27. It's very large, right? So there are very large numbers here. How does a controller do it? Again, by what we call batching. Like you batch requests of the same type such that they are sent one after the other. Good. Usually, just to continue completely with the scheduling things. Now I have assumed I did the batching. So I put the reads together and I put the writes together. Which one to start with, the reads or the writes? Is there any difference in the choice you make? So from a DRAM operation might not be much, but from a CPU perspective, and this is the interesting concept that I want to discuss with you, which one in fact matters to you? Yeah.
Like if you have this address that do an operation on that address, that right,
Good.
reordering that might.
Yeah, well, true. But always, we're talking about reordering to different memory locations. Always, if there are reads and writes back to the same location, you must honor, we call this consistency. You must honor the order, because otherwise, again, you mess with your, this is called data dependency, data hazard from the pipeline perspective. But assume they are all independent. Yeah. Memory control always handles.
Single person. Probably.
Thank you so much. True. So in reality, there is this concept. I guess you're raising your hand. You want the same thing, exact. Thank you. So the idea is reads. Think about when we talk about loads and stores. In a load, you are getting the data from a memory to the CPU. So the CPU is waiting for something coming from the memory. In case of a store, you are pushing the data to be written to the memory. So the CPU effectively is not waiting for anything, right? So this is why there is this terminology that stores, in fact, don't store the pipeline because there is no dependency whatsoever. I'm just storing something. It will go to the memory when the time it goes back. This is why when we're coming to the out order execution, stores are handled completely different than reads. In a store, you push it to a buffer. You don't even wait until it's being written to the memory and you declare it retired, done. Like I'm done with this store. Do it at your own convenient time in the background. I don't care. In case of a load or a read, that's not the case because I'm waiting for the data to come back. And there are dependencies where I'm reading this data to do something with it. To read is critical to the pipeline latency. So for that purpose, across the memory hierarchy, in fact, there's always a tendency to favor reads over writes, right? And for the cache allocation policy, right, back and that stuff, we'll come also into this, is that it impacts our cache design to also demote or deprioritize writes the caches.
Yes. How does that change when you do that, like some shared memory?
Yeah, a good point. So if you have coherency and then they're talking, but this goes back again to the point that reads and writes to the same location cannot be reordered. All what we're talking about is different memory locations. If you received read and writes to the same location, whether they are from the same core or different core, you must honor the order because otherwise you will mess around with the correctness. Yeah, pipeline doesn't, but the shared resources, the cache hierarchy, and the memory controller nodes, right? Because they receive the requests in a certain order, and they must respect. Good. Yeah, by this we are done. Thank you.
Address marking for the significant base will affect the locality.
But it will not affect locality, but it will try to use locality. We are saying for a locality application, the least significant bits change very frequently compared to the most significant bits. So now, how can I leverage this as the memory? The idea is if your least significant bits change the most,